So let's start at the very foundation of what mathematicians do. Remember, when we're looking at statements that mathematicians look at, we're trying to figure out, is it true, is it false? Do we try to prove, find a counterexample? Also, as we've seen in this class, sometimes there's statements that we're not quite sure until we start to run through some examples. And so one of the nice things about induction is that we could start making hypotheses and guesses of what we think might be true, and then use induction to prove that that might be true, or that that will be true. So let's ask this question. What is the sum of the first n positive odd numbers? Now, this is probably a question that you've never thought about. If it is, bravo to you. But if you add up odd numbers, what number do you get if they're starting from 1? So, for instance, if I look at the first one, I add up, so when I look at the n equals 1, so 1 positive odd number, the smallest one, I get 1. If I take a look at the sum of the first 2, well, 1 plus 3 is equal to 4. If I look at the first 3, this is equal to 9. If I look at the first 4, this is equal to 16. Look at the first 5, get 25. Now, hopefully, as an astute mathematician, you're like, haha, I see the trick, right? These are all even numbers. No, hopefully not. Hopefully you don't see that. These are all perfect squares. So we want to be able to state this as some type of mathematical statement that we can use induction to prove. Okay, so what we'd like to prove then is we'd like to prove that 1 plus 3 plus 5 plus all of these, I'm going to try to write an odd number. So if I think about the first n odd numbers, how do we even write that? What this left-hand side would be, how could we write that succinctly? So in this case, notice, it's sometimes easier to work with the larger numbers here. When n equals 4, the last number is 7. N equals 5, the last number is 9. So this should be 2n minus 1. So this right here, this would be the sum of the first n odd positive numbers. So that's what this left-hand side could be represented in using n. And then our hypothesis then is that n equals 3, the sum was 9, n equals 4, the sum is 16. This is going to be equal to n squared. We'd like to prove that this is true. We don't need this here. Prove this for all n in the natural numbers. So we will use our lovely skills of mathematical induction to prove this. So our proof, we're going to start out with a base case. So the base case, again, has to be true for the smallest value of n. Obviously, the smallest value of n we're working with is 1. So we will say, let n equal 1. Again, we work with the left-hand side first, which in this case, we only include the first number. Then we go to the right-hand side and we see, does that hold for n equals 1? So we see 1 is equal to 1 squared. Great. Base case is done. Easy. So if you'd like to make a statement over here, you can say the base case is true. So now we'll go to the induction step. So we will assume that 1 plus 2 plus 3 all the way up to 2n minus 1 is equal to n squared is true for n. We'll prove this is true for n plus 1. So again, we're just making this basically the structure of how we're going to be working with this induction step. We assume it's true for n. We'd like to show it's true for n plus 1. So now again, we work with this left-hand side. I almost always suggest working with this one that allows you to use the induction hypothesis easiest. So we're going to start with this. So we can see, notice, we have 1, notice by the induction hypothesis 1 plus 3 plus 5 plus blah 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 plus 2n minus 1, and then I'd like to go to the n plus 1, right? So if this is true for n, what does it mean if I plug in n plus 1? Well, that means I'm actually plugging in n plus 1 here. So I have 2 times n plus 1 minus 1. So this left-hand side, when you have n plus 1, this becomes 2n plus 1. So we have 2n plus 1, but because I knew that I was going to use the induction hypothesis, I stated it at the beginning. Most likely for you, you might end up stating it afterwards. Doesn't matter. But here, by the induction hypothesis, we know this is equal to n squared plus 2n plus 1. So if I think about what I've done is that I've replaced this sum. All of this right here is n squared by the induction hypothesis. And I just have this extra term here of 2n plus 1. And that's equal to this. So, since n squared plus 2n plus 1, well, what does this equal? Well, what are we trying to show is equal? Well, again, if we're trying to show that this is true for n plus 1, we're trying to get that this is equal to n plus 1 quantity squared. Does this equal n plus 1 squared? Well, yes, you're all factoring machines. So since this is equal to n plus 1 squared, we have shown this statement is true for n plus 1. So then, by induction, this is true for all n in the natural numbers. So again, we just have this concluding statement about how induction works, and then that concludes our proof. So we had this hypothesis that we based it off of by looking at some examples. We were able to come up with a formula, then we were able to prove it, and now hopefully you know that the sum of the first n odd numbers becomes n squared, which I think is a cool result. Now, one last thing I want to mention real quick about this statement, because when I introduced the proof by induction technique, I talked about this P of n. So what this statement is that we're referring to, because I say, down here, we've shown that this statement is true for n plus 1. Really, my statement, P of n, this says that 1 plus 2, or this was 1 plus 3, plus 2n minus 1 is equal to n squared. This is really the statement that I'm referring to in regards to n. So if you think about what is P of n plus 1, well then that's where we get 1 plus 3 plus 2 times n plus 1 minus 1 is equal to n plus 1 squared. If you were to try to prove something about, say, n plus 4, well then that would be 1 plus 3 plus 2 times n plus 4 minus 1 is equal to n plus 4 squared. So this maybe ties it into the original notation that we used. So that's what we're talking about, this statement being true for n plus 1.